We will be solving a question from Leetcode, that is 220. Easy question. It's a minimum bit flips to convert number. So let's first understand what the question is telling. A bit flip of a number x is choosing a bit in the binary representation of x and flipping it from either 0 to 1 or 1 to 0. Okay. So for example, for x equals 7, the binary representation is 1, 1, 1. And we may choose any bit including any leading zeros not shown and flip it. We can flip the first bit from right to get 1, 1, 0. Flip the second bit from the right to get 1, 0, 1. Flip the fifth bit from the right, a leading 0 to get 1, 0, 1, 1, 1, etc. Given two integers, start and goal, return the minimum number of bit flips to convert start to goal. Okay. So let's first see with an example. We have here an example of 10 and 7, right? So its binary representation is 0, 0, 1, 0, 1, 0 and 0, 0, 1, 1, right? Now its answer is 3. The answer is 3 in the simple case is that we need to go from 10 to 7, right? 10 to 7. So the thing here is that if you could see here, like if you could see here is that one thing, this 0 we need to convert it to 1, right? This 1 is 1 are same, no need to convert. This 0 and this 1 are different, so we need a flip. This 1 and this 1 we again need a flip. So here we need a flip, here we need a flip, and here we need a flip. So 3 is our answer. Why? Because the number of positions where the bits are different is our answer. That is what we need to find. We don't care, okay, what we will do to change any other bit. Like this 0 and this 0. If I would say this 0 and this 0, both are same. So why we need to flip it? There is no sense in changing the bit that are same. As simple as that. Here I have shown you only this 0, 0, 1, 0. Actually the bits, there are also leading zeros in both 7 and 10. But as they are same, we don't care. Okay. Now let's understand it with another example, the 3 and 4. Here we can see that this 1 and this 0 are different. There's one position. This 1 and this 0 are also different. Another difference. And this 0 and this 1 are also different. So our answer is 3. As simple as that. So we just need to find the number of total positions where the bits are different in both the number. And as the constraints are 1e9, we have to traverse till 32 bits, right? So we have a simple brute force approach that we will be discussing here. Okay. Now first, okay, you have been, let's say, given 4. Its bits representation is 1, 0, 0. There are also leading 0 that we are not writing. Okay. The thing is that I want to access this last bit. I want to access this first bit. Okay, second bit from last. I want to access the last third bit. How to get that? Because then only I will check the 3 and that ith bit from last, or let's say ith bit only. That ith bit, if ith bit of both the numbers are different, we have to change it and we will increase our answer. But the question is that how do we find this ith bit? So to find this ith bit, we have to understand first the left shift operator. Okay, so the people who know left shift operator, you can skip this section and you can move forward. Okay, so here we have, what does the left shift operator do? Right. Okay, so let's say we have a number that bits representation is something like that. Okay, 0, 1, 1, 1, 0. Okay. Now if I do this is like, okay, 2 raised to 0, 2 raised to 1 plus 2 square, that is 5. 5 to cube, 2 raised to 4. So it's the number is 21, right? The number is 21. Now if I write 21 left shift operator 2, what it does? It shifts all the bits left side by 2. What it means is that it multiplies the whole number by 2 square. it is what is it is happening. So the number now it will be converted to now. So let's say we have another 0 here. So we have 1, then 0, 1, 1, 0, and we know that okay there are two zeros, and as the 21 into 4, that is 84, right? It's 84. You can count this. Okay, so this is 2 raised to 0 into 0. Here is to 1, 2, 3. So we have 8, 8 plus 2 raised to 4, that is 16. 2 is 32, 2 is 64. So we are at 64. And you could check it is it's 22. It's my mistake. It is 22. 22 into 4, it is 88. And thus this is 88. Sorry. Okay, so it is how left shift works. It shifts all the numbers by how many you have written. If you have written 3, all the bits will be shifted by 3 positions. Okay, so okay, so now how we will be using, let's first understand this. 1 left shift 2, 1 was this, with left shift it 1 it is 0 1 0, with left shifted 2 it is 1 0 0. Okay, now why this information is important, how to check if the ith bit is set or not, just and a number with this. Like if we want to check the second bit, with 6, the 6 is 110, this 100 is this number. Okay, now so checks bitwise and it returns this 0 and 0 0 0 and 1 0 1 and 1 1. So if we get any positive number different other than 0, our bit is set. Yes, means if one left shift I and with that n number is not equal to 0, we are sure that that bit is set. Okay, so here is simple thing. So if one left shift I and n is not 0, then it is set, else it will return 0 as seen in below example. 1 left shift 3, 1 0 0 1. So we need the third bit, sorry, 1 2 3, right? Third is 0. So okay, 1 left shift 3 is okay. Okay, so 1 left shift 3 means it is this bit position. For ith position, so let's say for the first position, our I, like if you want ith position, we have to do and with 1 left shift I minus 1. Okay, just getting 0 0 means 1 left shift 0 means first position. Okay, just want to clear it. Okay, so 1 left shift 3 means we need to check fourth bit from last. Okay, we need to check fourth bit from last. Okay, so it is 1 0 0 and this is the fourth bit, that is it is not set, and we see it 0 0 0. Using this, we check all the ith position that were bits are different and we return total position. So let's get to the code and let's try this. What I need to tell. See, the one thing what we know is that how many total bits we going to check. There are maximum 32 bits as we have 29 maximum starting goal. So first see this for int I0 I less than 32, this is I. We just need to check, and this is our count. We need to check if our ith bit is set or not. So let's bit 1, bit of start. How do we get 1 left shift I and with what start? We get our bit, right? And bit 2 is equal to 1 left shift I and code. Now if it's simple, if bit 1 is not equal to bit 2, count plus plus return count, it will work beautifully. Why? Because see, if our starting goal as position is set, then let's say you are checking for second bit, so 1 left shift 1, so the number would be, so here what we will get if our bit is set, let's say this is our number, we want to check the third bit. Okay, so third bit is this one and here the 6 is set, so it will return what? It will return 1 left shift I only. So 1 left shift 2 is what? It is 2. it is like, okay, so 2 raised to 0 to 2 raised to 1, 2 square, it is 4. So 1 left shift 2, if I want to write 1, if I want to write 1 left shift 2, that is 4. If I want to write 1 left shift 3, that is 8. Simple. So bit 1, if both start and goal are, if bit 1, it is actually the number, it's not bit 1. Bit 1, the value of that will be 4 or 8, right? Or any, but the value of that is bit 1 or bit 2 is 1 left shift I, okay? And if they're not set, then bit 1 and bit 2 both will be what? 0. So just so if bit 1 is set, it will be 4. If bit 2 will be set, if this, if I equal to 2, and if bit 1 and bit 2 are set, if in the start and goal the both are set, then the value of both bit 1 and bit 2 will be 4. So they are same. Similarly, if both bit are not set, then bit 1 will be 0 and bit 2 will be 0. That's why, and they are same. So we have only one condition, that if they both are not same, increase our count. Because that may happen if this is set at I equal to 2, then this will be 4. But this will not be 4, it will be 0, as we have seen. So if our bit 1 and bit 2 not equal to same, if they are not same, then we increase our count. Let's run check it. Okay, so it's take time. Okay, so this compilation error. Okay, so this is need to be commented. So yes, it will be fucking. So now let's get to the another approach, that is using XOR operator. You may be knowing this operator. See, this operator is beautiful. Why? Because when the both bits are different, it returns 1. False true, it's true. True false, it's true for XOR operator. False false, it is false. True true, it's also false. This is how XOR operator works, and this is the most important thing. We will be using this. So here, when let's take an example of 10 and 7, we XOR it. Okay. XOR helps that if both bits are not same, that the 0 and 1 is not same. So here it is 1. If 1 and 0, sorry, if 1 and 1 are same, then it is 0. If 0 and 1 are not same, then it is 1. If 1 and 0 are, they are not same, it is 1. So this is our XOR. After doing XOR of 10 and 7, now what we need to check? We need to check the number of set bits in this XOR. That is very simple thing. That is where the simplest thing comes. The XOR operator time complexity is O of 1, and just we need to check the number of set bits in the XOR. That is our answer. So let's get to here. We go for bit 1, remove this, and XOR well, XOR answer, let's say the start XOR goal, and if bit 2 is something of XOR answer, if there is a bit, okay, if there is a bit 2, if it's not 0, then just go for it. This is XOR answer, and just check if that bit is set or not. Just run and check, and we will get our answer. Okay, so we have used XOR operator, we have used the before submission. There is something optimization. This is working 32. This loop is going till 32. But does it need to go for 32? Because in 7 and 10, we have seen that the leading zeros are not to be checked. It is not what. So what a second optimization we will be doing is that we will be using log. We will be using log operator, log2, max of start comma goal. Why it helps? See, log2 of 10, it will give us 3, right? Log2 of 10, here we go for 10 and 7, it will give 3. So it is telling that you check till 4th bit, I equal to 0, I equal to 1, I equal to 2, and I equal to 3. Here the important is it is less than or equal to. Understand? You don't need to check further, because 10 and 7, the further bits are already same. They are leading zeros. So this is a small optimization, and it will be fucking fun. In before approach also, when we were checking using without XOR, we can use this thing also, right? Okay. Now let's come to another approach, that is setting of the rightmost bit. Setting of the rightmost bit, right? Now, see, this is the only optimization done. Optimization no, but another way to count the number of set bits. For example, after doing XOR of start and goal, we are here. If someone asks you that you need to set the rightmost bit in O of 1, so this is an approach. You just do n and n minus 1. The number n and take n minus 1 and end with that. Your now the number will be the rightmost bit will be set off. See here, this was a bit representation. N minus 1 gave this, it's 0, 1, 1, 1. And it with 0 and 1 different, 0 and 1 different, 0 and 1 different. And see, we get all the 1 0 0 1 same, but this all 0. We are able to set this 1 to 0, right? So if someone asks you how to set the rightmost bit of any number to 0, we just need to end with n minus 1 and we are done. And we do this till we don't get n become 0. So this is an optimization in log 2, and also where the time complexity is just the number of set bits in the XOR value. Here the optimization, we don't need to traverse the 0 0 0 1 1 1, that is till 8. We traverse only 3 times, that is 1 0 1 1 0 0 0. Okay, so let's apply this approach and let's see. So XOR ans, so simple while XOR ans is not equal to 0, what we do is that XOR ans and XOR ans minus 1. We do count plus plus. Till my XOR ans is not equal to 0, I will keep setting off the rightmost bit. This helps in what? Setting off the rightmost bit in XOR ans. Okay, let's run and check. Yes, it is working fine. Okay, please try to understand and go with some examples. You will be able to understand why n minus 1 ending with n minus 1 helps to set off the rightmost bit. And there is another function, that is underscore built-in pop count, that is used to count the number of set bits. So instead of this whole drama, you could just write a simple function here. You got those XOR ans? Just use this built-in underscore pop count to XOR ans. This helps in the online assessment test where the speed is very important. In online assessment, the time is very crucial, right? So it is working fine. Yes, the time complexity of this function is also same. It is the number of set bits. Okay, XOR works in O of 1 time complexity. The space complexity is O of 1, right? Okay, so if you have any doubts, you can ask in the comment section. Thank you.